Okay, and today we're going to learn how to find the volume of a solid using something called the shell method. Now, the shell method is a little bit different than the other methods that we learned so far, and so I'm going to go through and break up. You need to find two radius for the shell method. You'll need to find the outer radius and the inner radius. So our outer radius here is from our axis of revolution to the top of the shell, which is in this case P plus W over 2. Then our inner radius is from the axis of revolution to the bottom of our shell, or the bottom of the representative rectangle, if you're not drawing the shell, if you're doing it in 2D. In this case, that's going to be P minus W over 2. Now, to find the volume of a shell, think of this as if it was a cylinder. If there's a cylinder, we'd take the volume of the outside cylinder minus the volume of the inside cylinder, or the volume of the hull. So our formula to find the volume of a single shell would be the volume of the cylinder minus the volume of the hull. So we're going to do some little algebra, and then so we only have to do this once, and then you can just simplify it down, because it does simplify pretty neatly. But I kind of want to show you the little formulas of how this formula come about. So volume of the cylinder, remember, a volume of the cylinder is pi r squared, that's the formula of the base, times the height, in this case of h, minus, because that's the volume of the cylinder. Now we're going to minus the volume of the hull, and the volume of the hull is another cylinder, and so that's going to be pi r squared h. So pi times our radius, but our radius is P minus W over 2 squared times h. All right, so a little algebra here. We're going to take the full method and figure out what P plus W over 2 times P plus W over 2 is. And when you work that out, you get P squared plus PW plus W squared, and we still have that times by the h. And then here we have, do the same thing but with the minus sign, so our sign in between changes. So that's going to be a P squared minus PW plus W squared times h. Okay, now let's just get rid of the parentheses by distributing pi h to each term. Don't forget to distribute our negative and also the pi and the h here. So here's what the cool thing about this formula is. Notice that our p squared pi h terms cancel out, and our w squared pi h terms cancel out. So we're left with just 2 p w pi h, and I'll write that as 2 pi. I'll write that as 2 pi p h w, which is 2 pi times the average radius, and then h stands for the height, and then W, which I forgot to write, it stands for thickness, width, but we'll call that our thickness, and that's going to be dx dy, okay, the infinitely small thickness. Okay, so how will this translate in? So that's just one shell. So to find the volume of the whole solid of revolution, we need to integrate this from A to B. So the 2 pi, that's a constant, so I can factor it out. I'm going to integrate from A to B, my beginning and my ending, my shaded region. And then I'm going to have P of x, which is our average radius, H of x, which is a height, and dx, which is our thickness. Okay, and of course this could be done in terms of the y variable as well. So let's see what this represents on a 2D object. First thing I want you to notice is that in this technique, the representative rectangle is always parallel to the axis we're revolving around. All the other ones, they were perpendicular. In our last method, they were perpendicular. Axis of revolution has to be parallel. Our representative rectangle is parallel to our axis of revolution. That is fundamental that you set it up that way when you do the shell method. Okay, next we're going to look at how do we figure out what P of x is. Well, P of x is the distance from the axis of revolution to your representative rectangle. That's your P of x or P of y. So here, that's P of y, because it's a y distance, it's a height. And in our last graph, this is P of x. It's an x distance away. Okay, notice this, it's just that distance that the representative rectangle is from that. A lot of times it'll be x, but not always. And a lot of times that P of y will be just that random y variable, that placement of it. but it'll change based on which axis you're revolving around. Okay, next thing we need to do is figure out how do we find h of x? Well, height is the length of your representative rectangle. So that's going to be this. This is what h of y, when it's the representative rectangle's horizontal, would look like. And then on the bottom graph, this is what h of x is. That's the height of the representative rectangle. So that's what you put in this blank. Now your thickness, and this will be an equation in terms of x or y. So this is always going to be some sort of equation you have to figure out. Your thickness is the how infinitely thin or thick your representative rectangles are. So if it's a horizontal representative rectangle, it's going to be dy. If it's a vertical representative rectangle, it's going to be dx. So that's how you determine if your integral is going to have a dy dx. All right, so let's start with this one. Now, you would probably have to draw the picture. I went ahead to save time, put the picture in. So we're going to find the region bounded by the curve y equals square root of x, the line x equals 4, and the x-axis generates a solid. Find the volume of it. Now, we did one similar to this already, but we revolved around the x-axis. Now we're going to revolve around the y-axis. So we're going to set it up the same way as we did. But notice that my representative rectangle is parallel to my axis of symmetry, so I got to use the shell method. So a formula for shell method is volume is equal to 2 pi. Now we got our shaded region starts at 0 and goes to 4. So from 0 to 4 of, now the distance that representative rectangle is from our axis, well, that's just x. Okay, and then the height, in this case, is just our equation, square root of x, and the width of our representative rectangle, which is dx. Okay, I'm going to do some simplifying down. X times the square root of x is just x to the 3/2 power. And then we can integrate this using the power rule. And now we're going to evaluate plugging in 4 in place of x minus plugging in 0 in place of x. I'm just going to simplify that down really quickly. Notice I factor out the 2/5. It's just easier to work with. You can do it whichever way you want. And I end up with, let's see, 4 to the 5/2 power is 32. And then multiplying that by 4 gives us 128 pi over 5. Try the your turn problem below. The region in the first quadrant bounded by the graph of the equation x equals 2y cubed minus y to the 4th, the y-axis revolving around the x-axis, set up the integral of the volume for the resulting solid. So you don't have to solve it, we're just going to set up the integral. So of course you wanted to start by drawing the graph, so sketching the graph of x equals 2y cubed minus y to the 4th, the y-axis and revolving around the x-axis. So on the left-hand graph, that's my shaded region that we have, revolving around the x-axis. And because we want to do the shell method here, we need to find our average radius. In this case, our average radius is simply y. Our thickness, our width is dy. And then our height is how high is our long is our equation, our represented rectangle. And so that's the equation. So volume is equal to 2 pi, the integral. Now we need to figure out our beginning and ending in the integral. Now to set this, you can set the equation 2y cubed minus y to the 4th equal to 0 to get the 0 to the 2. We can look at the graph. They figured it out in the graph. But this is how you do it if you did not have the graph already done. So our limits of integration is going to be 0 to 2. And we have y times by our 2y cubed minus y to the 4th times by dy. And that's it. That's the integral. That's how you would find the volume. Okay, number 2, we're going to do the same thing, but I chose this problem because it has some slight differences in the last one. We're just going to set it up. So I've drawn my 2 equations, the straight line and the parabola, and I want to identify my pieces to put in my equation. So we need to find the average radius. All right, so to find the average radius, we normally would say it's x. Okay, it's the distance this is from the axis. But remember, the average radius, you're looking for the distance the represented rectangle is from the axis of revolution. But since I'm revolving around x equals 3 here, this, what I just drew in the purple, is our average radius. And so 3 is that full distance, and I need to subtract off until I hit that graph So this full distance, and then subtracting the part off, this part here, until I hit the curve. And that curve I'm going to hit happens to be the parabola. So my average radius is going to be 3 minus x. So I'm going to subtract the x distance, whatever my x value is, to hit the parabola. My height is going to be how high is my representative rectangle. Well, to figure out the representative rectangle, it is the distance between our two graphs here. So if I go up to the line, it gives me this full distance, and then I need to subtract from that full distance up to the parabola. So x plus 2 is the distance here. Now I'm going to minus the distance to the parabola, which is the x squared. So our height is x plus 2 minus x squared. The last thing we need to figure out is the thickness of our representative rectangle. And our thickness is changing along the x-axis, so it's dx. So putting this together, our volume is going to be equal to 2 pi, the integral. Now, start to finish. So our shaded region begins. We need to figure out, we're in terms of x, we need to figure out our x values. Now, so I labeled it on the graph, but in case you don't, remember you learned this in Calculus 1. You set your two equations together to find where they intersect. So our x values of intersection is -1 and 2. So we're going to integrate from -1 to 2 of 3 minus x times x plus 2 minus x squared dx. Let me rewrite that a little. Let me zoom that out so you can see the dx. There is your equation. That's how you would set up this to find the volume using the shell method. Okay, and the last example I'm going to have you do is this one, but this time I'm going to actually have you solve it, not just set it up. So let's start by setting this up. So again, you should sketch your graph. Here's my graph of what it looks like. Now, first thing I realized is my representative rectangle needs to be parallel to the axis I'm revolving around. So I need to figure out my average radius. My average radius is the distance from the axis of rotation to our representative rectangle. So that distance is y. Then I need to figure out the height of my representative rectangle. So that's the distance, how long my representative rectangle is. In this case, it's up to from the axis to the equation. So it's going to be e to the negative y squared, and my thickness is dy. So volume is equal to 2 pi, the integral, my shaded region is from 0 to 1, that was given, of y times e to the negative y squared dy. Now this is another product, so I'm going to solve this using the U sub method. Okay, don't forget to change your upper and lower bounds. So my upper bound is now -1. My lower bound is 0. So V, my volume is going to be equal to 2 pi, the integral, and now it's going to be from 0 to -1 of y e to the u du over -2y. So the y's cancel out. I bring out the -2. The 2 outside with the -2 cancel out. So I'm left with just negative pi, the integral from 0 to -1 of e to the u du. Now recall that the upper bound must be larger than the lower bound. So since my upper bound is smaller, I need to flip my bounds and negate the expression. So I rewrite this as pi times the integral from -1 to 0, e to the u du. And then remember, the integral of e to the u is e to the u. So I have pi e to the u. Evaluate it from -1 to 0. So I start with the upper bound, replace the e with 0, the u with 0, and then replace the u with -1. And I get pi minus pi over e, or volume is equal to pi times 1 minus 1 over e.